Hello everyone, welcome to this tutorial. My name is Emerson Ahrari, I'm a Google Earth Engine specialist. In this tutorial I'm going to show you how to calculate evaporative stress index, a drought index already calculated and ready to use by Novo product. And this product available through Awesome GEE community catalog through this address. This product is a valuable product for the drought monitoring that give us estimation about the water availability or water consumption that's really useful for agricultural studies. For example, the values in this index ranges from negative to positive values. The positive values showing actually high water available for the agricultural activity and the negative values showing insufficient water for the agricultural activity. So, if you want to learn how to work with this product in the Google Earth Engine platform, actually follow this tutorial and also get important information about the drought and water consumption. So, and here this product available in the global scale with 4 km spatial resolution with weekly frequency, and it is available since 2001 until present. So I'm highly suggesting use this tutorial if you want to work on the drought monitoring or agricultural activity. So let's make a new Colab environment, and then I'm gonna show you how to do this procedure and get such kind of information from this product step by step. First of all, make a new web page and go to the colab.research.com. So here it is. Make a new notebook and then start coding. In the Colab environment, basically, we are scripting based on Python, and now I'm gonna establish a connection between Earth Engine and Colab environment. But first of all, we need to call the essential libraries. So start with Earth Engine libraries like EE and GEE map. Another library, Xarray, imported as a XR, because in this tutorial we want to convert the Earth Engine data collections into Xarray format. So another library that is not built-in available here is XEE, a revolutionary library in the Python allowing us to bring Google Earth Engine data into Xarray format and local environment in the Python that's allowing us to do a lot of further calculations on the satellite data. Let's import it again after installation, and remember to import essential libraries like NumPy and pandas as PD, and also import matplotlib.pyplot as plt. That is a basic library for the visualization and graphing purposes. Let's run the first cell. Now we are waiting until essential libraries installed successfully. Then we can start making connection between Earth Engine and Colab environment. If you faced with any challenge in this tutorial, feel free to put your comments uh, on my YouTube channel, and then I will reach them out as soon as possible. So now as you can see, all the libraries successfully installed. Clear the outputs, and now let's make a connection between Earth Engine and Colab environment. Already EE library imported. From EE, start with authentication, Earth Engine.initialize. Okay, now here, if you go on the net and search about the EEE, you will find a GitHub page, a detailed instruction about each EE library. As you can see, for initialization, here you will find the project and OPT URL. these two arguments necessary for initialize. Start with the project argument. Okay, every user has own project ID. Go to your code editor environment, the code editor environment in your account. So then you will find upper right the account information. Go to project info and here you will find your cloud project ID. For example, mine is like this and you will find yours. Just go to this address and find yours and add it into your code. The next argument based on instruction is OPTURL. OPTURL is a fixed address available here. Just copy and paste into your code. The Earth Engine now, the Colab now asking permission to access to your Earth Engine account. Now the permission granted by clicking on continue and your Earth Engine account. After a few moments, you can see the connection established, meaning that from now on, I can use the Earth Engine capabilities and functions and data catalog here and also do the rest of the processing easily without any challenge. So, in the next step, I'm gonna define the region of the interest. First of all, create a variable like map. From GEE map, another library already called here. So, call map function with a satellite base map, just like this. Let's run the map and then you will have a user interface including a satellite view that allowing you to select your region of interest. In this tutorial, I'm gonna actually work on Iran, my own country, and I'm gonna actually show how ESI or evaporative stress index varies over this country. So I need to call a shapefile that's showing the Iran's border. Some administrative borders available on the Earth Engine platform. First of all, I need to locate my country through a marker. Remember that you can use this tutorial for your own region of interest and also you are not forced to do this tutorial based on location I'm working. You can use all of these techniques for your own region of interest. In the next step, we need to have this point as a variable. So, for example, the ROI sets to from the map, select the last feature and convert it into a single geometry. Now you can see the ROI now the point available as a variable. In the next step, I need to find the FAO simplified administrative unit layer. This product available in the Google Earth Engine platform. You can find it easily by typing the dataset titles. Okay, now here there is a feature collection snippet. Just copy and paste. My region of interest here is Iran. Iran sets to make a parenthesis like this and paste the feature collection. As this is a feature collection including the country's border, I'm gonna show only the uh, area actually including or actually intersected with the point, with the ROI point. Filter bounds, select those shapefiles actually overlapped with the ROI and convert it into a geometry just like that. So to make sure the Iran selected or not, so here map.add layer allowing to visualize the result. So visualize Iran without any visualization parameter. The layer name is Iran. Let's run. After a few moments, you can see the shapefile of region of interest. In the next step, I'm gonna actually do all the processing based on this area. So now make a new cell and call evaporative stress index dataset here. So this product, as I mentioned earlier, available through Awesome GEE Community Catalog and this address. So image snippet available with 4 and 12 weeks actually, the frequency, the 12 weeks temporal format, or 4 weeks, but 12 weeks considered in my study. So we create another variable. For example, here we are working in the Earth engine for now, and that's why I'm gonna actually call this image collection and then filter it to a period of time. As I mentioned earlier, this product available since 2001. For example, I'm gonna have it from 2010 or from 2001 even, from 2001 to 2025. So, and it is filtered based on a period of time, and then we want to clip it based on Iran shapefile. Let's make a loop structure and also an unknown function using lambda added into the loop, each input considered as img and each image clipped based on Iran border, and then copy properties img.property names. Let's run. So now, as you can see, the collection is running. We want to make sure how many product is available. More than 100, more than 1,200 product available for this period of time. And here you can see ESI, evaporative stress index, with existing metadata file available for each date separately. So this is the data collection format upon the Earth engine. But from now on, we want to actually uh, get the collection out from the Earth engine and bring it into the Python using XEE library. So now collection, I'm gonna actually use the Xarray structure to convert an image collection into Xarray format. From XR, called the open dataset, the input data is the collection based on from Earth engine and CRS. The coordinate system will be EPSG 4326. Geometry, region of interest is Iran, and the next parameter is about the scale. Spatial resolution is 4 kilometer, but here I'm gonna actually resample it to 10 kilometer because I'm working in a country scale and I need quarter spatial resolution to speed up the processing. And also in the national scale, the general pattern and general changes is important, at least for me, not very detailed information. So let's run. Okay, the data set. Here you can see still we have 1247 images or 47 arrays during the time in the different dimensions, temporal dimensions, longitude dimensions, and latitude dimension. There is a variable here, the ESI with 3 dimension already mentioned. Okay, this is a multi-dimensional structure or Xarray format. You can here see what's the main difference between image collection format and Xarray format. So now in the next step, I'm gonna actually select one of the images randomly and plot it to give you some visual insight about the values in this product. So let's go next, and from the data set we want to actually select one of the images through the time dimension sets to, for example, the image numbered 100, for example. Here selected, the variable is esi.esi, and make a plot for that image. X-axis sets to longitude, y-axis sets to latitude, robust sets to true to avoid outlier impacts on quality of output. Here you can see a range of positive and negative values. First of all, the image clipped based on the border, and the next thing is about the range of the values. In the ESI or evaporative stress index, the positive values showing actually uh, higher water consumption or higher wetness compared to the long-term average, and the blue areas or negative areas showing lower ESI value or showing lower wetness or dryness compared to the long-term average. So as you can see here, actually the negative values uh, showing insufficient water and positive values showing sufficient water compared to the long-term average in this single date. So the pattern will be changed based on the selected time. For example, in another image, the pattern of value will be changed. For example, in this date, in the whole of the countries, we had negative values that shows the actually the drought condition or areas actually suffering from water stress. So in the next step, I'm gonna select one single point and monitor the data or water consumption variation through the time. So now make another cell and new variables created, latitude and longitude. Go to the code editor environment. My study area is my country, Iran. So water consumption is my target of interest in this context. So I prefer to select agricultural area and see and check about the water consumption during the time. Through the marker in the northwest of Iran here, near to Urmia Lake, we have actually a region, actually a big areas for agricultural activity. Through a marker, I will select this area, and here you can see the longitude and latitude. Just select and copy paste it. This is longitude and this one is latitude. So the next we want to actually select the values uh, available in this point through the time. Point sets to from the data set select latitude point sets to latitude, longitude sets to latitude, the nearest point to the selected actually coordinate considered. Print the point, and here you can see the single value detected through the time for this point. Let's make a plot then. So the variable ESI must be selected earlier. Dot ESI and make a plot. After a few moments, you can see the ESI values through the time. So here it is, positive and negative values in this point. Values greater than 0 or positive shows the wetness, and the negative values showing the dryness. High water, actually sufficient water, positive values, or insufficient water, the negative values, compared to the long-term average. So let's convert it into a data frame or table format. So data frame, get the point and convert it into a data frame structure. If you faced with any challenge in this tutorial, you can find the code link below this video on description box. Let's run the data frame, and here you can see the ESI values from 2001 to 2024. So as the temporal variation only matter in this tutorial, and latitude and longitude is same for each row, we can actually skip them from the further analysis. Just select the ESI column and let's run, just like that. Okay, now in the next step, I'm gonna show you how to make a plot for this, actually, for this result. It is very easy to do here. So call the figure and x, two variables, sets2 from plt, call the subplots. I want to have a figure with this size, for example 8 and 3. So let's run, and here we have an empty plot. So in the next step, I'm gonna actually plot uh, the data frame value, the df index, df dot index, and the df values. This is the actually change of the values through the time. But it would be better if actually we show we showing negative and positive values in two different color. It is easier to interpret, just same as the previous example I already showed you. It is really easy to do in the Python. Just let's first we need to separate the positive and negative values. For example, two variables, positive and negative, needed here. So from the input data frame, select values greater equal than 0. So, and from existing data frame, select values less than 0. Let's run. The positive values only showing the values greater than 0, and negative showing values less than 0. Okay. In the next step, I'm gonna actually make new plots that showing the positive and negatives in different color. For example, the first one color should be black, just like this. The next plot is positive values. The positive values could be in bar, could actually show with bar graph. Positive dot index and positive, and color should be blue because the positive value showing the wetness, the higher water consumption compared to long-term average. Tab blue is better. X.bar again, this one negative values with a red color, because actually the red color showing lower water consumption or insufficient water or the dryness. The widths, the bar widths could be, for example, 20. Let's run. There it is. And let me to reduce the thickness of line widths, sets to 1, for example. Yes, now it's really better, or 0.5. Even we can increase the size of the plots in width and height. There it is. And here, as you can see, we can actually monitor the times when the water availability is sufficient or when it is insufficient. For example, in the selected area, in the last 5 years, we had a critical situation about the availability of the water resources for agricultural activities, and that's actually showing a kind of drought stress in this area that should be considered in the further studies. You can use these techniques for a same tutorial for actually another regions in all around the world to get a better insight about the water consumption in your own region of interest. I hope you liked this tutorial as much as I did. Thank you for your attention.